Hello children, welcome back to the channel. Today we will be taking up the topic of planetary motion. So, what we will be discussing is simply that how the planets move around the sun. Now you know that astronomy is one of the oldest branches of science because in the earlier days, in the long time back also, people used to gaze the sky and try to understand how the heavenly bodies, as they called it, the stars, the planets, the meteors, the comets, used to walk. So, based on those empirical observations that people made, uh, initially what appeared to people was that the Earth was the center of the universe and everything used to move around the Earth. And that was the model of the sky that was given during, say, 1st century AD by Ptolemy. So that model was known as geocentric because the Earth was the center of the universe. It was given by, of course, Ptolemy in the West. However, nearly 400 years later, this was 1st century AD. Nearly 400 years later, that is around say 498 AD, in India, and around 1543 AD in the West, two scientists, Aryabhatta and in 1543 Nicholas Copernicus. Came to the conclusion by their observation, empirical observation, that Earth was not the center of the universe, but actually the Sun was the center. Now, Sun is of course not the center of the universe, but Sun is the center of our solar system, right? So this model, because Sun is the center, was known as heliocentric. Now the question arises, if Aryabhatta came to this conclusion in around 500 AD, why we give credit to Copernicus? It's just because of the fact that Copernicus worked in the West and the Western scientists were not aware of Aryabhatta's work till even later. That is, say, around 19th and 20th century. So, even though Aryabhatta came to the heliocentric model much before, nearly 1100 years before Copernicus, but the Western scientists came to know about the heliocentric model or tried to come to terms with heliocentric model only in the 16th century AD. Okay, so it was a big jump actually from geocentric model, which was accepted in the West for nearly 1400 years. Now, when the heliocentric model was given, people didn't like it much, but still a lot of studies went on. Particularly one scientist, Tycho Brahe, dedicated almost his entire life to the study of the planets and their motion through the sky. And based on this, he made a huge collection of observations. And studying those observations later, in just before the time of Isaac Newton, Kepler came up with 3 laws that governs the planetary motion or motion of the planets in the heliocentric model or in our solar system. And these 3 laws are known as, number 1, law of orbits, number 2, law of areas, and number 3, law of time periods. Okay, on law of periods. Law of periods. Please remember, these laws predates Newton's law of gravitation. However, Newton's law of gravitation became instrumental in trying to establish or mathematically proving these 3 laws, and that is why we studied the laws, Newton's laws of gravitation, before Kepler's laws. But Kepler's law predates Newton's law of gravitation. That needs to be remembered. Now, before going into the second and third law, what does the law of orbit says? It simply says that the planets move around the sun in elliptical orbits. Okay, so if any planet of the solar system is taken, it will move around the sun in an elliptical orbit, and with the sun at one of the foci. We know that an ellipse has 2 foci, right? Now, sun will lie either one or the other of the foci. Let's say this is the focus where the sun lies. So, according to Kepler, based on the observations, empirical observations of Tycho Brahe, what he gave first law is that the law of orbits, that the orbit of a planet around the sun is elliptical. Okay, we are not trying to go and prove this particular law, but the next 2 laws we will try to find and establish from Newton's law of Newton's law of gravitation. Okay, so if we accept Kepler's first law that the orbit of a planet is elliptical, let's say this is the elliptical orbit and the sun is at one of the foci and planet is in the orbit at some position in the orbit. So this line joining these 2 will give us the distance or the position of the planet with respect to the sun. Let's say this position be called r, vector r. Okay, so Newton's law of gravitation will give us that force between the sun and the planet will be equal to minus g, mass of the sun, mass of the planet, by r squared, and it will be directed opposite to the opposition vector, that is, the force will be directed in this direction. So we have taken negative of r cap, because r cap we know is the unit vector in the direction of r. Or we can rewrite this as minus g m by r cube into r vector, because we know that r vector can be given by r into r cap, or r cap will be given by vector r divided by r. So we substituted this with vector r by r, so we get this particular result. Okay, if it is so, what will be the torque acting on the planet P? By definition, torque will be r cross f. F is the force of gravitation here and r is the position vector, right? So r cross f. And so if I take this part, which are scalar, right? So I take minus g m by r cube outside, and then we get r cross r, vector r and vector r here. But we know a cross product of a vector with itself is a null vector or zero vector. So this will be a zero vector, which means tau, which is also given by dl by dt. All these results we have found in our previous discussions of rotational motions. If you haven't seen those videos, I suggest you refer to them. The link will be given in the description below. Okay, so tau is given by dl by dt, and so dl by dt is a zero vector, which will give us that angular momentum must be a constant. So angular momentum of a planet moving around the sun will be a constant. This result will be very handy in proving Kepler's law, second and third law, particularly second law. So first we have found this result. So what we'll do, we'll keep it aside for the time being, that L is equal to is a constant, both in direction as well as in magnitude. Okay. Now we are in a position to try to prove Kepler's second law, that is law of areas. So what it states, we will see in a while, is that let's consider the planet is initially at this particular position and it is moving in the counterclockwise direction, say, which means its velocity vector will be along the tangent in this direction, right? Let's call this V. After a small time, say delta t, this planet would have moved along its orbit by a certain distance, and say it reaches this particular point. Okay, and let's call this point P dash, and the velocity at this particular point will be along this tangent, right? Which will be V dash, V prime C. So what it appears is that this radius vector from Sun to the planet, it will form a triangle or sweep the triangle, this particular triangle, delta S P P dash. Okay, so Kepler's second law, or the law of area, says that this radius vector joining the planet to the sun sweeps out equal areas in equal intervals of time, which means that if the planet moves by, if the planet sweeps out certain amount of area, say A, in a given time delta t, the next delta t time it will sweep out again the same area. So if I say the planet was at this particular point at some point of time, after a time interval of delta t, it will be here, so that this area and this area are equal, or anywhere else. So in equal interval of time, equal area will be swept out by the radius vector. Okay. Now, if I look at this, what will be the area swept out? Say the area vector will be, we know from cross product, will be this cross the second vector P dash, P prime. Now we will assume delta t to be so small that the velocity vector can be supposed to be constant. It doesn't change for a very small period of time. That we always can do. And so we will have R instead of P dash, this distance will be, if initial position was R and the final position is R plus delta R, then this distance will be delta R. So R cross delta R, which will be equal to half R vector cross delta R, can be written as V into delta t, because this distance swept out will be with a velocity of V but in a time delta t. So this will be V into delta t. Okay. Or we can rewrite this as half R cross. Now we know one thing, that if the planet has a mass m and velocity v, its momentum, linear momentum, will be given by p, which means velocity v can be given by momentum divided by mass. So we can write p by m into delta t. Okay. So doing certain cross multiplication, delta A by delta t must be equal to half into R one by twice m, say, into R cross P. Okay, but we know that R cross P is the angular momentum, again from the previous chapter. So we can write this is equal to angular momentum by 2m. That is to say, delta A by delta t is a constant. Why? Because L is a constant, we have just seen. So what it means is that the vector area swept out per unit time. So area per unit time, and so this is known as aerial velocity. Like distance per unit time is speed, displacement per unit time is velocity. So area per unit time is similarly is known as aerial velocity. So aerial velocity of a planet is constant. It doesn't change. So the radius vector will indeed sweep out equal areas in equal intervals of time. Now for the third law, or law of periods. So for the third law, or law of periods, what we will assume for simplicity is that the planet is moving in a nearly circular orbit, because circle and ellipse are conic sections. So if the two foci coincide, then the ellipse will reduce to a circle, and so we will assume that the planet is moving in a circular orbit, which means that the magnitude of the radius vector will remain the same. So if I say Sun is at the center and planet is here, then the force of gravitation will be Gmm by r squared, which will be the same everywhere. Now this Gmm by r squared is the only force acting between these two. So the planet is moving in the circular orbit, and let's say its velocity is given by v, and its magnitude of velocity is given by, speed is given by, velocity is given by vector v, and speed will be given by v. Then this force will give you the required centripetal force to keep the planet moving in the circular orbit. And so this must be equal to m v squared, where v is the velocity, magnitude of the velocity, by r. Right? So centripetal force is given by mv squared by r, and this centripetal force is provided by the force of gravity, Gmm by r squared. So if we equate these two, and then we will have v squared must be equal to Gm by r. Okay? Now, if the object moves with a speed of v, a path of radius r, then we know that v can be given by 2 pi r by t, where t is the time period of rotation. That is the time taken for the planet to start from here and move and come back to point P. Okay, and 2 pi r is the circumference of the planet orbit. So v is 2 pi r by t. So what we have, substituting v with 2 pi r by t whole square must be equal to Gm by r. That is to say 4 pi square r square by t square equal to Gm by r. So cross multiplication will give us t square must be equal to 4 pi square by Gm into r cube. Now this term, four pi square by Gm is a constant, and if so, then we have t square is proportional to r cube, which is nothing but the statement of law of periods, which says that the time period of the square of the time period of rotation of a planet around the sun is proportional to the cube of the average radius of the orbit. So since the orbits are actually elliptical, so what we will do, we will average out the radius, and whatever value we get, cube of that will be proportional to t squared, or square of the time period. And just for the sake of remembering, time period of the planet around the sun is nothing but the year in terms of that particular planet. In Earth it's 1 year, that is 365 days. Other planets we normally measure it with in terms of Earth years or Earth days. That how many days of Earth, what's the Earth days required for the planet to move in the complete one revolution. For example, for inner planets compared with the Earth, that is maybe for say Mercury, we say in terms of Earth days. For outer planets like Jupiter or Neptune or Pluto, or not Pluto, Neptune or Uranus or Saturn, we speak it in terms of Earth years.